Okay, moving on. Chapter 26, Transition Metals and Coordination. So start off talking about gemstones, and if you look at two different gemstones, mainly ruby and emerald, they're both made by, well, the color is made by chromium ions, chromium plus 3 ions. Also, a ruby is actually a sapphire, aluminum oxide is sapphire, but iron and titanium is responsible for the blue color and blue sapphires. But chromium for ruby, but it's also in the beryl for the green color in rubies. So let's talk about transition metals in general. They're very different than the main group elements. And generally speaking, they have high melting points, high density, and pretty tough hardness. And they tend to be good electrical conductors. I mean, this is not true for all of them. Obviously, mercury is not a very high melting point, and there's other metals like thorium that have really high melting points. But in generally speaking, there's a wide range of physical properties here. And but the similarities are in the electronic structure. So in valence electrons, valence, remember, means the outermost electrons, and that means the highest n. And the 4s is higher than the 3d, so it goes 4s to 3d and 5s to 4d and so on. So the s orbitals are actually higher. They're more outside. They may be lower energy, but they're valence, so the outside electrons. In electron configuration, generally speaking, there's two electrons in the s orbital, I just mentioned, and then the smaller principal quantum number for the d. And some exceptions for this. So the exceptions for this are the chromium and copper. You can see that they have. It's very common for the s orbitals to jump in to have the complete d shell. So in the case of chromium, it goes for the single electrons in the d orbitals, and then of course the for copper goes into the double. And copper, silver, gold all have similar electronic structures, and they're also very unreactive. So they're noble metals. So, but in general, the S and the D and the N minus 1D tend to be pretty closely spaced in energy. So there's not a big, vast difference between them. So that's the reason why the properties of the metals are very relatively consistent. So let's talk about atomic radii. And generally speaking, the trends are actually a bit opposite. So if you look at the radius fits it because it gets bigger going down. But the second and third row, they're about the same size, which is kind of weird. And this is known as the lanthanide contraction. And the reason for this lanthanide contraction is from the f orbitals. So after you get to the lanthanum, those orbitals, those elements have the f orbitals. So it goes to lanthanum, and then it goes to the complete f shell, and then it keeps on going over. So if you look at the periodic table, so the f orbitals besides the first d, but then the f orbitals fill, and you have that full f orbital shell, and what that does is it shields the nucleus from the positive charge. So, but it's not. I'm sorry, it's not as good. Beg your pardon. It's not as shielding. It's not as good at shielding, and so then there's the greater effective nuclear charge, and it pulls in those valence electrons more. So sorry, I misspoke. The f orbitals are not as good. And then because of that, if you look at the ionization energy, we actually have the reverse trend where the third row has higher ionization energy. But if you compare that to the other elements, it doesn't go this way, right? So this is kind of the opposite in a way. So that's kind of weird about the. Well, it's explainable, but I mean it's kind of weird about the periodic trends of them. And similarly with electronegativity again, but that's because of the really attractive positive center of the atoms, at least relative to the other ones. And you get another change. And I always thought it was really cool. The gold actually has a pretty high electronegativity. I always wondered what kind of cool stuff you could make with a gold. Gold is that peak there on the green peak on the right. So, but just daydreaming as a student, I suppose. Okay, well, let's talk about oxidation states. So if you look at this image, the darker colors are less common, and the brighter red is more common. And something you might notice right away is that almost every element has a +2 oxidation state, well, except for scantium. Scantium just has a +3. But the the +2 is from the loss of the s electrons, and but also +3 is very common, losing a d orbital and the other two electrons as well. But you, point of this picture though is not necessarily is that it's just that you can see there's a wide range. Look at manganese; it can go from +2 to +7, right? And same thing with iron. It can be, we're familiar with a +2 and +3, but it can go up to +6. So that's another weird thing about these transition metals. They have lots of different oxidation states. Okay, so let's start talking about how they're weird, the oxidation states. Let's talk about crystal field theory. So let's talk about complex ions. So it's complex. It means it's got more stuff around it, and the stuff we give it a name, we give it a ligand. And what is a ligand? A ligand is a Lewis base that donates electron density into the central metal, and that whole thing is called a, well, when you combine it with other ions, it becomes a coordination complex. So the oxidation number of the metal, this is known as the primary valence. The secondary valence is also the coordination number. It usually ranges from 2 to 12, but 6 and 4 are most common. 4 can either be square plane or tetrahedral, and 6 being octahedral. So, and you see the cobalt with the 6 ammonias, that would be an octahedral complex. So this would be a complex because this whole thing is this cobalt with 6 ammonias that's going to be +3 charged, that whole complex together, and it's combined with 3 chloride counter ions. Oh, just like right here in the next picture. Oh. So, and this is where the ammonias there act as Lewis bases. They're donating electron density towards that cobalt center, but the whole thing still has a +3 charge, and then they have the counter ions to have the charges be evened out. So, and we mentioned that, and it's a covalent bond, sharing of electrons, a coordinate covalent bond. I mean, is it a single bond? The electron density is being shared. I mean, there's a and it becomes a molecular orbital. So I know we're using Lewis theory here, but it is. I mean, I think of the electrons in terms of like this kind of fuzzy cloud that kind of float, that kind of exists in many different places at once. So I don't necessarily say there's 2 dots connects to a silver, connects to a nitrogen. I just see these electrons being shared between the nitrogen and the silver metal complex. So, and we talked about, well, we've already talked about these single bases. Now there are some that have 2 sites that they can attach to, and if it's 2 sites, it's known as bidentate. So 2 teeth, so extra teeth in the bidentate, and these bidentates. There's other ones, but this one here is ethylene diamine. So ethylene, the ethyl groups here in the middle, right? And then the diamine, 2 amino groups there, so the nitrogens. So that is the ethylene diamine. If you go by the naming convention, it's bidentate because it had the electron, the lone pair there in the nitrogen can act as Lewis bases. It can act as Lewis bases in 2 sites on the metal complex. So we'll talk more about that later. Also, we can talk about chelating agents. So here are some common ligands. Water is a very common ligand, and they actually, many metal ions in water, like iron and aluminum, form complexes and act as weak acids in solution. Ammonia is another one, chloride, carbon monoxide, cyanide. Ammonia is pretty. Like if you put ammonia with complexes, sometimes the solution gets really pretty in color. So thiocyanate, oxalate. This is a bidentate ligand, ethylene diamine. Ooh, and then we have ethylene diamine tetraacetate. So commonly known as EDTA. You'll see EDTA written on bottles. So ethylene diamine tetraacetate. So and there's also ethylene diamine tetraacetic acid is the acid that comes along that. So it has 6 sites that it can go on, and this is also known as a chelating agent. Chelate means claw. So it's like this molecule here. It's like a big hand, and it claws around the metal ion. And these are very useful. EDTA is a very useful molecule. You can use it to remove things like lime and rust. So there's certain products that you can use. You can spray on things. So if you want to get rid of rust color or lime color or like the lime. So like also like magnesium and calcium stearate. So soap scum, you can get rid of soap scum by this because the chelating agents will pull out the calcium and magnesium ions and then wash it away in solution. So we'll talk about these later. You can use this for other types of heavy metal poisoning. But you probably, I mean, this is something you want to avoid though because it'll also strip the metals out of your bones. So, okay, so here's some with polydentate. So, cobalt with three ethylene diamines. So this is the one on the left here, and this one, and the next one is cobalt with EDTA. So that's the chelating agent. That's the claw. That's the claw coming and ripping that solution, ripping that ion out. So at least that's what I always kind of think about, the claw coming in and like a big bird coming and ripping that ion out of whatever compound is there. So here's some geometries. This shouldn't be too surprising since VSEPR. So two things is linear. So that's really the only option there. Four things can either be square plane or it can be tetrahedral. So we'll show you the hybridization later. Six things octahedral. So how do we name things? So first of all, you name the ligands alphabetically, and the prefix, the mono, di, tri, tell you the number of each ligand, and then write the name of the metal cation. And if it's a charged one, and you put the oxidation state, and if it's an anion, drop the ending of the metal and add 8 to the end of it. So, for instance, so the ligand here, bromo, chloro, hydro, cyano, nitro, oxalato, and for water, aqua, amine for ammonia, carbonyl for carbon monoxide, ethylene diamine, sometimes just said En. And same thing with the anion complex here. Chromium becomes chromate, cobalt, cobaltate, copper, cuprate, gold, orate, iron, ferrate, lead, plumbate, manganese, manganate, molybdenum, molybdate, nickel, nickelate, platinum, platinate, silver, argentate, tin, stannate, zinc, zincate. So just to pronounce some of those words, quite a bit of a mouthful. So let's name some of these things. First one, CrH2O5, Cl, Cl2. So water is aqua, Cl minus is chloro, and the chromium is chromium 3. So there's 5 waters, so that's penta aqua, chloro, chromium 3 for the plus 3 of the chloro, and then with the counterion chloride. So penta aqua for the 5 waters, chloro for the chlorine, chromium 3 for the plus 3 ion, and chloride for the anion. So penta aqua chlorochromium chloride. So, and if you haven't noticed, if you ever have to spell these out in a Word document, it'll always yell at you because I bet you that's not in the dictionary. So let's do the next one. So we have an anion. So potassium is the metal. So you're going to say that first. And then you have iron. So it's going to be ferrate for the iron. So ferrum for ferrate for the iron, and cyanide or cyano for the cyanide. And there's 6 of them. So it's going to be hexacyano. So the whole thing is you say the word potassium, and it's going to be hexa 6 cyano for cyanide ferrate, and 3 for that. So 3 for the minus 3 ion. So it's potassium hexacyanoferrate 3, and 3 being the negative 3 charge. So hopefully this is not your first lecture coming in, but I guess I'm sure you know isomers are the same number and type of atoms, but they have different connectivity. Stereoisomers, they have the same connectivity, but they are mirror images of each other. So then they are optically active. And this should be a review for you in general. And except for, I guess I guess you can look at the isomers of the structural isomers. It's just with the ligands; they're in different places, and linkage isomers they're joined in different ways. Stereoisomers, they were, well, we already mentioned the optical isomers. The geometric isomers, you can have cis trans in the square planar geometry. Also in the octahedral, if the azimuthal is if the z-axis, the top and the bottom are the same. Also, you can have fast Mayer. We'll talk about this soon. So let's talk about linkage isomers first. So here in this compound on the left, you have the nitro, and then the one on the left, it is connected in the nitrogen atom. The one on the right is connected in the oxygen atom, and there is actually a bit of a difference here. So the first one, so it's five ammonia, so pentaamino, and then just nitro for the NO2, cobalt 3, and then same thing but a different connectivity. So it's pentaamino but nitrido cobalt 3. So different connectivity. And if you have it connected in different spots, so for NO2, if it's on the nitrogen, it's nitro. If it's on the oxygen, it's nitrido. For cyanide, if it's on the carbon, it's cyano. For the nitrogen, it's isocyano. For OCN, it's the cyanado ion. If it's there in the oxygen, it's cyanido. For the nitrogen, it's isocyanido. And for thiocyanates, if it's on the sulfur, it's thiocyanado. And if it's in the nitrogen, it's isothiocyanado. So it's the regular and then the iso for the isomer. And geometric, you have cis-trans, and we'll talk about cisplantane later. So, but it's a cancer drug. So you're going to have cis and trans, and of course the cis can be polar, and the trans is going to be nonpolar for as far as the physical properties. So you can have a square planar. You can also have cis trans and octahedral if the top and bottom are the same. So the z-axis, the azimuthal axis, whatever you want to call it, top and bottom. You can see here along the equator, equatorial plane, the xy plane, there you can have cis-trans isomerization. But you can also have Foss and Mayer. So Foss means for face, and I guess I always think of it kind of like I guess for crystal structures. If you look at those three atoms, like the three chlorine atoms, they form their own plane. As I always kind of pictured it like a plane there with just those three atoms in it. Whereas if you look at the Mayer, actually the three atoms, if any 3 points create a plane, I mean that's basic geometry, but there's going to be more atoms in the Mayer. The Mayer is more it's an arc. So for Fast, I think of it like a slice with a three centers forming a plane, and the Mayer I see is like kind of like a sort of a semicircle in it. So however you want to remember it, that's how I remember it. So, but however it works for you. And optical isomers, we talked about this. If there's mirror images, there's other that are not superimposable. Kind of like your right hand and your left hand are mirror images, but they're not superimposable upon each other. And let's move on and talk about valence bond theory. So this is it's. If you remember talking about valence bond theory in the first semester of chemistry, it turns out this theory is not entirely true, but I mean it really deals with electron pair repulsions. So it explains the geometry, but it doesn't really get the color and magnetic properties. And we'll talk about that in terms of the electron orbitals soon. So it has to do with the repulsion of the different electron clouds. So here's a review for the hybridization, and also with the metals, you can get the square planar one looks new, right? The DSP2. You can get square planar geometries out of that. So the crystal field theory, and these charges. We can predict them by the group numbers. Yeah, we know about that. That's already pretty common. And the representatives, we only have one type of charge, but and the transitions metals, though, they have multiple types of charges, and they're not as easily predicted. So a little different. And so let's look at these pictures here. If you look here, we have in this case it's an octahedral complex around, and you can see it's in you have the octahedron there, and inside of that octahedron you have the d orbitals. And in this case here with the octahedron, and that means that the things around the octahedron are really going to affect the dz squared and the dx squared minus y squared, because those are along the x, y, and z axes. And so these ligands are going to really push on those orbitals, and they're actually going to raise them in energy. And not really so much though for the other ones that I always see these kind of clover leaves outside of the plane of bonding. So these ones here, they kind of miss them. Although later on we talk about tetrahedral, the tetrahedral affects those greatly. So tetrahedral affects more the dxy, dyz, and dxz. So that's going to come later. So, and this is kind of what I've said already. It's going to push on these, and it's going to raise the energy levels, especially for the dz squared and the dx squared minus y squared orbitals. And that's what we have here. And depending on the size of the splitting, we have certain consequences of this. And the colors that we see, and that comes from the electrons leaping. So visible light typically comes from, well, colors in solution and metals and things come from visible light and electron energies being absorbed. And well, went too fast. So let's talk about some complex ion color here. And here you have kind of I guess is a blue purple sort of color, and the absorbance there is gonna. So if you look at the color wheel, it should be in the blue purple end. This means that it should be more absorbing on the sort of yellowish end of the spectrum. And I mean, it is kind of in the yellow. It looks like the peak is closer to blue green, but it's the opposite end of the. I guess it's a reddish purple. I don't know. I guess it is a reddish purple looking at it more now. I guess the reddish purple is the opposite is the yellow green, and that's where it is. So this is not exact. I mean, our eyes are not spectrometers, so a lot of this is also art as well. I mean, literally art, like mixing colors. And so let's look at this one. Two ligands form complexes with particular metal ion. When the metal ion complexes with ligand A, this resulting solution is red. When the metal ion complexes with ligand B, the resulting solution is yellow. Which of the ligands produces the larger change in energy? So we have to go back here. So if it's red, the opposite of red is green, and the other one's yellow. The opposite of yellow is violet. So that means that the max absorbance is going to be along the. So for the red one, it's going to be green. For the yellow one, it's going to be violet. And so it's absorbing more. The violet is higher energy, so that means that that one is from the bigger jump. So this one's going to be B, because violet is larger energy photon than green. So, but let's talk about the crystal field strength. And well, I guess we mentioned this already, that the energy of the photon is the size of that. So the size of split, and that's where the colors come from, basically what this slide says. But let's talk about the different strengths. Not including this carbonyl, like carbon monoxide. It's pretty strong. I can't remember if it's stronger than cyanide, but it's close to the strength of cyanide. But strong field ligands are those. And the weak field ligands, water's kind of in the middle, but halogens, water tend to be low. And also the size energy gap, the cobalt has a larger energy gap than all the way down to manganese, for instance. So the bigger, and The split of this energy level depends on the strength of this crystal field. So the stronger the ion, the splitting field of the ion, the bigger the energy split is. And if there's a big split, then the electrons are going to stay in the lower energy one. So it just goes by Hund's rule. Not Hund's rule. I'm sorry, the Pauli exclusion principle. Right, you have the Hund's rule, and you start with the low going up. If it's a big split, it's going to fill in the lowest electrons, and if it's a big gap, it's going to stay in the lower ones. If it's a small gap, it'll go into the higher one. If it's a small gap, that's known as high spin. If it's a big gap, it's known as low spin. So if you see here in the next picture, if it's a very large gap, and if you remember Hund's rule and the Pauli exclusion principle, so you start filling up electron energy levels, and if you pair up the electrons, it releases something called the pairing energy. So if the energy gap is bigger than the pairing energy, then of the electrons, it's going to stay in a low spin complex. If the gap is smaller than the pairing energy, then it's going to go into what's known as a high spin complex. So that's if there's a low energy split. So we have the high spin and low spin, and so what? Well, the low spins are diamagnetic and magnetic properties, and the high spin are paramagnetic. So it changes the magnetic properties of the ion. So, or the complex, I should say. It's not just the ion. And tetrahedral is similar to octahedral, but they go for it causes the splitting's bigger and the ones outside the plane, like I talked about before, dxy, dy, xe, dyz, and these tend to be higher, and they're usually, well, they tend to be high spin. So for here, um, they're like that. So like kind of like I said before. And so other things, so square planar, the square planar, these are almost always low spin. So the splitting tends to be bigger for these. And so what do we use this stuff for? So importantly, you can use it to extract noble metals, mainly silver and gold, with cyanide. So this is one of the ways we do it here in the United States. We get some gold heavy things and we kind of make heavy mud, and then we soak it in cyanide and strip out all the silver and gold and all the good metals out of there. You can also use mercury, but we tend not to do that in the United States. Other countries can use mercury, which is a horrible practice, but it's still done today. You can also use carbonyl for nickel. And I mentioned this before for heavy metal poisoning, so EDTA. And this is not something you want to do because it's going to make your bones brittle as well. Chemical analysis you can do for chemical analysis. We tend not to do this as much though because we tend to use more spectroscopy. It's much easier in this day and age to use spectroscopy and other types of techniques than using wet chemical techniques. But it's been done in the past. Other things, so biomolecules. So our bodies use chromium, manganese, molybdenum for various things. Iron, of course, for oxygen transport. We use it quite a bit for hemoglobin, and copper as well. So, copper to make hemoglobin. So you can see here where it's used, and various things. And we can also do selective ligands to analyze certain ions, coloring mixtures, so hexacyanoiron in 2 and 3 for that. It's kind of fun to do some of the art with that. That's fun to do, the photography and whatnot. And other biomolecules, so porphyrins, for instance, use porphyrins, and also cytochrome and hemoglobin, so other ones that have different metal centers. And the heme makes me think of the Beyond Burgers. They have their own heme groups. Those are good. Chlorophyll with the magnesium center. The light excites that, and it makes a high energy complex. Then it can do the energy for some chemistry and some anhydrases, so they catalyze water and carbon dioxide. So this is important to get dissolved carbon dioxide in the blood. And I mentioned for cisplantin as anti-cancer drug. This is interesting because what this drug is, it's an alkylating agent. It can mutate DNA, but it's kind of a mild mutator of sorts. There's it's a mutagen. This is a mutagen. Mutagen mutates DNA. There's much more powerful mutagens. Another alkylating agent that's really horrible is mustard gas. It's similar. It's a blistering agent, and I mean, besides the horrible, painful blisters you get from it, it'll probably give you cancer down the line. So you can get cancer from alkylating agents, and then you can be treated for cancer with alkylating agents. And I always thought that was interesting. But this is kind of it's a weaker one. So, but there's many other types of chemotherapy out there. But okay, so we are done then for this chapter. Thank you for listening.